But what we saw just a moment ago was that x equaled r cosine of theta. Look, when we were graphing in example 3, r was always some function of theta. We could replace our r with f of theta and see that x would be f of theta times the cosine of theta. Very similarly, the conversion formula y equals r sine of theta, well, guess what? We could make an adjustment, say that r is equal to f of theta, plug that in. Now we have x in an equation in terms of theta. We have y with an equation in terms of theta. This is very similar to what we were just doing very recently. Just the other day we were taking derivatives parametrically. We're going to do that now. dy dx, the other day we saw it was dy dt all over dx dt. Well, guess what? Our y is in terms of theta, so is x. Remember to do your derivatives this way, otherwise you'd have to memorize the formula on page 680 in our book. That's ridiculous, really. We're going to talk about horizontal tangents. They are going to occur when the top is 0, when the numerator of our derivative dy d theta is 0, and the denominator is not 0. Vertical tangents occur when the denominator is 0 and the numerator is not 0. And the case 0 over 0 requires further investigation. We mentioned the other day that we would need L'Hopital's rule to work that derivative out. But let's very quickly do example 5. Example 5, find the slope of r equals 2 sine of 3 theta, where theta is equal to pi over 6. Tell you what, let's start off by writing x is equal to r cosine of theta. Well, my goodness, you know what r is? According to what we see up here, it's 2 sine 3 theta times the cosine of theta. So here's my x completely in terms of theta. Look, we're going to take a derivative here. We can take dx d theta, and we're going to need the product rule. The product rule, take your first function, 2 sine of 3 theta, multiply that to the derivative of the second function, plus the derivative of the first function. The derivative of sine is cosine, but remember the chain rule. The derivative of sine of 3 theta becomes cosine of 3 theta, but a 3 comes out when you take the derivative of the inside. You'll have 6 cosine of 3 theta times the second function. So this is really what we have for dx d theta. Very, very similarly, we could work out what dy d theta is. Well, tell you what, let's do a little bit of work here first, sorry. Y is going to be r sine theta. And of course, that's going to be replacing r with 2 sine 3 theta times the sine of theta. We can take our derivative of y with respect to theta now. Again, guess what we have to do? We have to do the chain rule. Well, I'm so sorry, the product rule. The chain rule is a part of the derivative of the first function. But using the product rule here, we'll take the first function times the derivative of the second function. The derivative of sine is cosine. Then we will say plus, well, the derivative of 2 sine of 3 theta. Well, my goodness, you know what? We just did that a second ago, didn't we? That's 6 cosine of 3 theta times that second function, and here we go. Well, what is dy dx anyway? Well, we saw it's dy d theta all over dx d theta. And essentially, we're just going to recopy this. We just found dy d theta. That's 2 sine of 3 theta times the cosine of theta plus 6 cosine of 3 theta times the sine of theta. Down below, we have dx d theta. You could bring your negative out in front there. Negative 2 sine of 3 theta times the sine of theta. Plus 6 cosine of 3 theta times the cosine of theta. Well, one more thing, we're going to have to evaluate this when theta is equal to pi over 6. Well, let's do that real quickly. dy dx, the slope of the tangent line. We'll plug in pi over 6. 3 times pi over 6, by the way, is pi over 2, isn't it? And the sine of pi over 2 is 1. So I'll say 2 times 1. Now, the cosine of pi over 6 is radical 3 over 2. Let's continue working here. Again, cosine of 3 theta. Well, that's the cosine of pi over 2 in here. But we all know the cosine of pi over 2 is 0. So this whole second part of the numerator just becomes a 0 when we substitute pi over 6 in. Down below, again, the sine of 3 theta, it's going to become the sine of pi over 2. And we already said that the sine of pi over 2 is a 1. Well, what's the sine of pi over 6 as we're plugging that in? Well, a 1/2. And very similarly, just as we saw before, cosine of pi over 2 is a 0. Well, let's simplify. Cross out our 2's, cross out the 2's here, and what are we left with? A radical 3 all over a negative 1. Wow, the slope of our tangent line is at negative root 3 when theta is equal to pi over 6. We could find out what point of tangency that is by plugging in pi over 6 into our x and our y formulas. Normally we want to think about tangency with a point, with an x comma y. And of course we could just substitute that pi over 6 in there and very quickly work out what ordered pair in the rectangular sense we have. Well, we have one more example that we're going to be doing, and I'm just going to begin to set it up for the sake of time. For example 6, we're going to do the same thing. We just want to find derivatives. So let's very quickly say that x is equal to r cosine of theta. And of course that's going to be, in this problem, 2 plus 2 cosine of theta times the cosine of theta. And very similarly over here we could say y is equal to r sine of theta. And we'd have 2 plus